As the title implies, we are going to investigate today if you can balance a pop can on its edges. Why a pop can? I'm in the Rust Belt. That's what we call it here, pop. It's not a soda, it's a pop. Welcome back to the shrine. As you can see, I've got here an empty can and I have a full can. The idea is that we got an edge here and we have another edge. And so if we apply the can, if we set it up on those two edges and let it go, will it balance? Well, you can see that the full can, when I balance it on the edges, it's going to tip over. Now these are essentially two different brands, as you can see, but size-wise they almost identical. So here is an empty can, as you can see, it was open, it's empty. I'm going to set it on the edges like so, let it go, and it tips over. So the question becomes, when the can is filled with liquid at a specific level, is it going to balance? So let's get some liquid, put it in a can, and see if it's possible at all. So first of all, I'm going to apply a containment vessel. There's the can. As you can see, it's empty. Here's a calibrated cylinder. This is a 50 milliliter. So first, we're going to start off at 30 milliliters. So let's pour 30 milliliters of water. This is just tap water. Again, let's see if the can is going to balance. Okay, I'm going to set it on the edges, let it go, and you can see it tips over. So now I'm going to pour the water into the can, 30 milliliters. Now I'm going to set it on the edges again. Long and behold, the can is balancing. I really want to turn this like so you can see it from a different angle, but as you can see, the can is balancing on the edge. Well, if I move it too much, obviously it will tip over. So some water poured out, but I've got a theory that if I put more water in, it will still balance. So what I'm going to do is I'm going to put in a total of 200 milliliters of water. So I already have 30, I need to add 170. So here's 50. Here's 50 more. This makes it 180. And let's put in 20 more. So there's the 20 mark, plus minus 1 or 2, you know, tolerances. We live in a real world. So now we should have 200 milliliters of water in the can. So this is a 12 fluid ounce can. It can hold 355. Again, we only have 200. So let's see if I set it on the edge, if it's going to balance. And as you can see, at 200 milliliters, the can is still balancing. Now you might say that I flattened the edges at that point. Okay, but you can see it's not flattened, it's completely round. And we can try to put it in a different position, so we can put the opening at the top and try it that way. And you can see that it still balances. You can see that when I let it go, the water inside is going to slosh, so that will create a little bit of movement of the can. But once that surface stabilizes, the can is absolutely stable. Here I can turn it 90 degrees. You can see there is some water here at the edge, so not all the water is inside, and it is moving back and forth a little bit as the water sloshes inside, but it is still balancing. So I can put this at 90 degrees rotated, and you can see it's slowly moving, but it is balancing. So here's another position. When I let it go, you can see it rolls on the edge, but it still stays balanced. Yeah, if you're seeing this first time, you can tell everyone this is PFM. Just Google PFM for the acronym. Here's another side view. You can see it just slowly rolls, but it will stay balanced at the end. And I think the rolling is due to the CG. There's something about the tab here is throwing off the balance a little bit. But the point is, the can is not tipping over. It has water inside, and yet it stays balanced. So again, here's a full one that you can see it's not open yet, and when I put it down, it will tip over. It's not going to balance. Here's a can that is empty, and I put it down there, let it go, and it will tip over. So it's not going to stay balanced. So what is the limit? Obviously we saw that at 30 milliliters it will balance, and at 200 milliliters it will balance. I'm going to put in 30 milliliters more, so we should have a total of 230 milliliters in the can. So we got 230 milliliters in the can, and then we can try it again. And as you can see, it tips over. So the can empty is unstable. When it's filled up, it's unstable. But when it has a certain amount of fluid in it, it will stay balanced. So what is the physical background, you might ask? Let's go and investigate it with a mathematical model. The mathematical model was built in Creo, which is a well-known 3D modeling software. First, I scanned the can from all the sides. Then I built a 3D model where the external surfaces were aligned with the 3D scan. As you can see, there is good agreement between the scan data and the parametric model. The wall thickness of the can is not uniform. I cut up several cans and measured the wall thickness of the aluminum. By the way, this is the thickness of the aluminum can and the plastic liner. But I assumed aluminum thickness only. We can go and do a cross section. I measured 0.1 millimeter at the sides, 0.24 at the top, and 0.3 at the bottom. Accordingly, you can see that the model has a step here I did not bother adding a blended feature. The can has a tab on the top, as you can see. In Creo, we can go and do a query for the mass, and the mass of the can is 13 grams, which is the same what I measured with the scale. In this model, I have an assembly. The can is assembled with the liquid inside. You can see the can model here, and this is the liquid model. The liquid has a density of 1,000 kilograms per cubic meter, which is the same as water. There's a curve on the bottom here that is tangent to both of these edges, right here and right here. So this curve is tangent to the edges. This is how the model is constrained to the horizontal plane. This vertical line represents the vertical or the plumb line. The fluid inside essentially has the same 3D model, but I added a Boolean operation. You can see here, it's called a cutout. And essentially subtracted the can model from the fluid model. This way, the fluid contour inside the can perfectly lines up with the can contour, as you can see here, or in the bottom. So it mimics the contour of the can. There's a cut feature inside the fluid, and I can edit that feature, and you can see there is a dimension here. And if I modify that dimension and regenerate the model, you can see the fluid level goes up or it goes down. In Creo, we can measure just about anything. In the analysis mass properties, we can do a preview, and it is going to show the mass of the assembly. As you can see, it's 145 grams. So this is the mass of the assembly at this fluid level. One of my favorite pastimes is to misuse software. In the software, you can also do a sensitivity analysis. This is similar to an Excel goal-seek analysis. In the analysis, we can modify one dimension, like the height of the water column, and see how the volume changes. So we can just go click dimension here, click the extrude feature, and modify this dimension. We're going to go from 1 millimeter to 110 millimeters, and in the same time we can plot certain parameters. These parameters are coming from mass properties analysis or measured feature. So for example, we can plot the volume of the fluid as a function of this dimension. So here I'm gonna require 100 steps, and then in the options preferences I can animate the model. When I hit compute, you can see it will start off from 1 millimeter height, and then it will calculate the fluid level at every millimeter increment all the way to 110 millimeters. And in the same time, it is showing how the volume is changing inside the can on this chart. So these are the volume units, it's cubic millimeters. You can see it will get up to 350 something. So that's reasonable. The can holds 355 milliliters of fluid. I can also go and turn on coordinate systems, and what I did here is I added a coordinate system that is in the center of gravity of the assembly. So it's the can and the fluid. The coordinate system for the center of gravity is right here. Now I'm going to go and restart the simulation. And watch how this coordinate system is traveling as the fluid volume is increasing within the can. So you can see that it is creating this curve, and earlier on I exported the x and y coordinates of this coordinate system relative to this coordinate system on the bottom that is in line with this vertical line that I mentioned earlier. So from this picture we can see clearly that if the coordinate system falls on the right side of this vertical line, then the can is going to tip. And if it's going to fall on the left side, the can is going to balance on these two edges. I can go and rerun the analysis, and instead of volume, I can choose the x and y measure for the distance. You can see the analysis will run again, and it's plotting right now the y measure, the vertical measurement from the bottom plane of the location of the center of gravity. So the analysis is completed, and you can see here's the y measure and here's the x. I can go and export it to Excel, and we can post-process the data in Excel. So here's the data in Excel. You can see the iterations here. This is the volume in cubic millimeters. I converted into milliliters, something, more tangible. And then this is the distance x. So I'm basically plotting the distance x from the right side support, and then I'm charting the volume in milliliters. So you can see how the volume is changing as a function of this distance. Now remember, the coordinate system is pointing to the left, so whichever is the positive number, that's what we can use. So you can see here's the 0. These are positive numbers, these are negative numbers. So realistically, if the can has 22 milliliters of fluid or 230 milliliters of fluid, it will balance. As you might remember, on the experiment I used 30 milliliters and it was balancing. I also used 200 milliliters and it was balancing. So I gave a little bit of tolerance to myself, but this is basically the mathematical representation of the can. Again, here's a picture of the can. This is the coordinate system relative to which I measured the distance of the center of gravity, and you can see that x is pointing to the left. So if this number is positive, then it will balance. If it's negative, it will not balance. And you can also see on this curve, so the portion of the curve that falls left side relative to the vertical line, that's where the can is going to be stable, and to the right side the can is going to tip over. Well, that was one of my greatest tricks in my sleeve. Hopefully you guys watch it this far and enjoyed the video. I hope you guys liked the video. So next time you're in a break room or in a cafeteria, you can do this to the choice of pop you are drinking. So when you open the bottle and drink some of it, you can start balancing it. You can be sure that when the can is about half full, so it's about 175 milliliters, then it should be able to balance on its edges. So you can amaze your coworkers with your newly acquired knowledge. If you like the video, please give me a thumbs up, and if you like the channel, please don't forget to subscribe. And if you want to see more videos like this, please share the video with someone you think might be interested in this black magic. See you on the next one. Bye.